Hello. I guess it's a bit weird to start with a summary, but I didn't get to the summary of the electromagnetic wave chapter last time, and so let me just summarize what we did last week. So we looked at Maxwell's equations, which are the crown achievement of 19th century physics describing electric, magnetic, and optical phenomena. And there are four equations in this set of Maxwell's equations. The first one is that the electric charges are the sources of the electric field. That's Gauss's law for the electric field. There are no magnetic charges, which is Gauss's law for the magnetic field. A changing magnetic field or flux induces a circular electric field, which is Faraday's law. And finally, a current or changing electric field or flux induces a circular magnetic field, and that is Ampere's law. Then a consequence of Maxwell's equations is that there ought to be transverse electromagnetic waves which are emitted from charges if these charges are accelerated. And the propagation speed should be given by this equation that if you multiply c squared with mu naught and epsilon naught, this should be equal to 1. And that implies a propagation speed, or c, of 3 × 10⁸ meters per second, which is identical to the speed of light. And of course, as for all waves, the speed of light equals the frequency times the wavelength of the electromagnetic waves. If there are plane sinusoidal waves, then the electric field amplitude and the magnetic field amplitude are related by the speed of light with this formula. Electric and magnetic fields are perpendicular to each other, and because it's a transverse wave, they're perpendicular to the direction of propagation. There's a very large electromagnetic wave spectrum, and we can define a Poynting vector, which is the cross product of electric and magnetic field divided by mu naught. And this will point in the direction of propagation, and the magnitude of it will give the intensity of the electromagnetic wave. Electromagnetic waves also carry momentum, and therefore they exert radiation pressure on anything that absorbs them or reflects them. Electromagnetic waves are used extensively in human communications in the modern world. So now let's start a new chapter, and I'm going to challenge you with a little puzzle. You're probably aware that if you look in the mirror image has left and right switched. So how come it doesn't have up and down switched? And this is true even if you lay on the side or tilt your head, up and down is never switched. So I'm going to tell you the answer at the next lecture. So if we look at a very smooth surface, like in this picture, we discover an image of the world, or a reflection, which seems to be fairly faithful to the original. And to analyze such questions, we use the ray model of light. So in spite of the previous chapter, for the time being, we are going to ignore the wave nature of the light, and we simply define rays like we did for other waves, meaning that rays are perpendicular to the wavefronts. So this is for a circular wave, and this one is for a plane wave. As long as the light travels in straight lines, this ray model does well. So you can think of a ray also as an extremely narrow beam of light. And as an example, if you look at a pencil, you can imagine that the pencil emits many, many light rays, and a small bundle of them enters your eye, and then you can see it. Like any model, the ray model is an idealization, and we neglect the wave nature of light. However, we can describe reflections, refractions, as well as the formation of images by mirrors and lenses. And the description or this model is geometric, so the subject is often called geometric optics. If we remember from the wave chapter that the law of reflection is that if we define an angle of incidence, which is the angle between the incident ray and the normal or the line that is perpendicular to the mirror or reflecting surface, then the law says that incident angle must equal reflected angle. And of course, the reflected angle is the angle of the reflected ray with the same normal direction. And this is how it looks like in a three-dimensional picture. This law effectively holds only if the surface is very smooth. So if you have a rough surface, like so, then the law is still valid. However, because each ray reflects off a slightly different part of the surface, and therefore the normal of those little pieces points in many different directions, the reflected rays seem to go and bounce in all directions. And that is called diffuse reflection. If we have a smooth surface, however, then all the normals point in the same direction, and a bundle of rays like this will all get reflected at the same angle. And this reflection is called specular reflection. So what does smooth really mean? For the ray model, smooth means infinitely smooth. So since all things are made out of atoms, that would mean that mirrors are not possible, because at some points there are atoms and at other points there are not. And this is not a perfectly smooth surface anymore. However, since light waves are really waves, if the smoothness is correct up to the extent of about the wavelength, then that's good enough, and therefore mirrors are possible. So this is just a philosophical problem. You can, of course, imagine mirrors to be of continuous matter distribution rather than consisting out of atoms. So we have specular reflection if the surface is smooth, and diffuse reflection if it's not. From now on, we look at specular reflections. And let's start with an example. So let's say we have two flat mirrors which are perpendicular to each other, like shown in this diagram. And an incoming ray of light makes an angle of 15 degrees with the first mirror, as it's shown in the picture. And the question is, what angle will the outgoing beam make with the second mirror? And to find the answer, we first need to find the incident angle of the problem. So the incident angle of the problem is the angle it makes with respect to the normal. Copy this scheme here, this sketch here, then the normal direction is this. So this is the incident angle. And this angle is 15 degrees. And that means that, that the incident angle, which is called theta 1 here, has to be 75 degrees. Now, if we look now at the bottom sketch, we of course know that the reflected ray has to have the same angle, theta 2, with respect to the normal. So theta 1 equals theta 2. But we can now also draw a triangle going from the first point of reflection to the second point of reflection and making a right angle here in the middle. And because this is a right angle triangle, that means that theta 2 plus theta 3 plus 90 degrees must be equal to 180 degrees. Or theta 2 plus theta 3 must be equal to 90 degrees. And that means that theta 3 is 90 degrees minus 75 degrees, or 15 degrees. So the incident angle for the second reflection is 15 degrees. And now we can find theta 4 for the reflected outgoing beam. So that is the same as the theta 3 law of reflection. So it's also 15 degrees. And if we want to find the angle it makes with the mirror, that would be theta 5. And that means it is 75 degrees. And in this case, we also observe that the incoming and the outgoing rays are parallel to each other. Let's look at light reflections in the real world. So here I have a box that makes 5 light rays, and I can hold a mirror in there, and if I tilt it slightly, the normal of the mirror is I'm indicating here by this paper. But we can see that the angle of incidence equals the angle of reflection. So now let's look at images from a plane mirror. When we see an image, or when we see anything, our brain always assumes that light travels with straight rays, so it doesn't take into account the reflection of any surface. Therefore, even though the object itself is sitting down here, and the light rays just get reflected into our eyes by the means of the mirror, what we actually see is the light rays coming from those points over there. So we have a bundle of rays being emitted, for example, here from the bottom and here from the top. They reflect off the mirror and then enter the eye. So we have the real object, and we have an apparent image of it that is not real, which we, for example, we cannot touch it. We can calculate where the position is of that image, and to do that, we observe that this triangle, which is a right triangle, formed from the bottom of the bottle to the plane of the mirror to the point of reflection, that this triangle is congruent to that triangle, which is the equivalent thing connecting the bottom of the image to the other 2 points. And the reason why it's congruent is because these 2 angles, incident and reflected angle, must be equal. And the reflected angle, it repeats itself here behind the mirror. And therefore, this angle is 90 degrees minus the incident angle. And this angle is 90 degrees minus the reflected angle. And so we have an angle that is equal in the triangle. Then by construction, the angle here and here are right angles. So we have 2 angles that are equal. And the 2 triangles share one side with each other. So we have 2 angles on one side, and that means that the triangles are congruent. And if they are congruent, then the distance from A to D, which is the distance of the object to the mirror, must be equal to the distance from D to C, which is the distance from the plane of the mirror to the image. So image and object are at the same distance from the mirror, just on opposite sides. And this image is a so-called virtual image. And the reason why we call it virtual is there are actually no light rays in this portion. Those are just imaginations or constructions by us seeing the image. No actual light travels from here to here because it's behind the mirror. So then the image is called a virtual image if that is the case. So let's make an example. Let's consider a 1.6 meter tall woman who stands in front of a vertical plane mirror. And the question is, what is the minimum height of the mirror and how close must its lower edge be to the floor if she's to be able to see her whole body? And we assume that her eyes are 10 centimeters below the top of her head. To solve this problem, again geometrically, we construct several points on that. First of all, point A is her foot, then point G is the top of her head, point E is the eyes, F is the top part of the mirror, B is the bottom of the mirror, H is the top of the image, C is the bottom of the image, D is in the plane of the mirror, just like before. And we also construct a point M, which is at the same height as B. So this is a right angle here. And we observe that the triangle formed by M, A, and B, so this one, is congruent to the triangle M, B, and E, or that one. And the reason is, as before, that we have this angle here must be equal to that angle there. These two angles are right angles and are therefore equal to each other. And they share one side. So we have two angles on one side, and that means that the triangles have to be congruent. And if they are congruent, that means that the distance from A to M must be the same as the distance from M to E. Since E is the height of her eyes, and it's 10 centimeters below the top of her head, so that's 1.5 meters off the floor. And that means that B or M have to be at a height of 0.75 meters. So we've already solved the part how close the lower edge has to be to the floor. It's 0.75 meters. We can now similarly define a point N between sitting in the middle between G and E, and repeat the same exercise. And then we find that this point N and point F, which is at the same height, must be at 1.55 meters. And so the minimum height of the mirror is 0.8 meters, or the difference between 1.55 meters and 0.75 meters. There's one part that we didn't really consider. What if a person is a three-dimensional object, and so the eye is not exactly at the same distance to the mirror as the feet? So if she had really long feet, then actually the bottom part of the mirror has to be longer than shown here. However, as long as we consider just one plane for the object, one distance to the mirror, in other words, the formulas are correct. So we are now returning to the beginning picture of the chapter, which shows this reflected image and the real world simultaneously. And the question is this photo correct, or is it actually upside down? And at first glance, you would think we can't tell. So I can turn this picture around, and at first glance it looks to be exactly the same, but then you notice some differences. First of all, in this case, the people in the background are right side up, and here they are upside down, and there's no equivalent. And if you look at the image of the sun, this image is clear of the branches of the tree, and this one is not. And of course, this one is the same as that, since it's the same picture, just rotated. So we can now draw a sketch of the scene and find out which is actually the correct orientation. So here we have the branches which are between the camera and the sun. Otherwise, we couldn't find any such a case where the sun shines through the branches. And so in the case of the reflected ray, the reflected rays stay clear of those branches, and they hit because they are lower than the direct rays. So it is the direct image of the sun that shines through the branches, which means this is top, or this is top. And the picture indeed was upside down. For a similar reason, the people appear only on the bottom here and only on the top. And that reason is, as discussed before with the length of the woman's feet, the perfect correspondence between mirror image and object is only true if you consider just one plane. So we have different depths different distances to the camera for the branch, for the people, and for the sun. The viewing angle gets changed a little bit, and you can tell the difference between upside down and right side up. So now it gets more complicated. We now bend the mirrors, and instead of just a plain mirror, we take out a section of a sphere and cover it with reflective coating. And then two such mirrors are possible. This one is called a convex mirror, and this one is called a concave mirror. So for the convex mirror, the reflective coating is on the outside of the sphere. And for the concave mirror, it is on the inside of the sphere. And so for the convex mirror, if we have rays from a distant source, they diverge afterwards, because the normal, which of course always intersects with the center of this original sphere, is changing like that. And I can actually show you that in the real world. If I go back to my little ray emitter here. So here I have a convex mirror, and you can see that the reflected rays are going to the outside. If I look at a concave mirror, however, the rays converge rather than diverge. So if we have concave mirrors, then parallel rays seem to be focused into one point. So all five rays, they meet in one point. And that point is called the focal point. If you look very, very carefully, maybe I can zoom in here. You actually see that this focusing isn't quite perfect. One of those rays doesn't quite go to the same point as the other ones. And that is called spherical aberration. So if we draw a perfect picture, especially for a large mirror, those rays that are far away from the center of the mirror, they meet in a slightly different point than the focal point. So the bigger you make the mirror, the bigger is the spherical aberration, and the mirror is then not quite perfect. So another observation we make is that objects always have divergent bundles of light rays, but if they are far away, then they look almost parallel to each other. And therefore, since we know that such parallel rays get focused into one point, we can actually form an image of at least distant objects. So to find the focal length, or the distance between focus and the mirror, we again look at a little bit of geometry. So we have this triangle here. This triangle has two angles that are the same. This angle must be the same as that angle, because it is the triangle is constructed between two parallel rays and one line intersecting. And that means that this distance CF and the distance BF must be the same. If you have a triangle where two angles are the same, then two sides also have to be the same. And that means that the triangle is formed from the center of the sphere. I'm sorry, I forgot that part. So this point is actually the center of the sphere. Therefore, this angle must be equal to that angle, since a line drawn from the center of the sphere is always a normal direction to the spherical mirror. So this angle equals that angle, and this angle equals that angle. The two angles are the same, and these two distances are the same. The distance CF and the distance FB And if we now assume that the mirror is small, meaning that B is not too far away from A, then we can approximate the distance BF to the distance AF. And the distance AF is the focal length, the distance between focus and mirror. And the distance CB is, of course, the radius. For the approximation that the mirror is small, these two distances, which are equal to each other and must add up to the radius, we therefore get that the focal length is 1/2 of the radius. That's an important thing to remember for the spherical mirror, that if you know the radius, then the focal length is 1/2 of that radius. And to form the location of images geometrically, we can construct such images by using 3 type of rays. First, we look at a parallel ray. So here we have an object given by a bottom point and a top point. And if you have a parallel ray, then it gets reflected through the focal point. That's the idea of focal point. The second type of ray is, instead of making a parallel ray, we make a ray that goes from the object through the focal point, and that becomes a parallel ray. So this is ray number 2. And then finally, if a ray goes in the direction of the center of the sphere and the object, then this gets reflected on itself. And so those 3 rays then meet in approximately one location, and that is the location of the image of this object point here. If we look at the point O, all 3 rays are identical to each other, and they all reflect on top of each other. And so we just assume that the image location for the bottom is then at the same distance from the mirror as the top. Let's now calculate where the image is, rather than just constructing it with a sketch. So the same object with a point O prime and a point O. And now we have to consider more triangles. There's actually also a 4th ray we can draw. And that 4th ray goes to the center of the mirror. And at the center of the mirror, this spherical mirror behaves like a plane mirror, meaning the normal is just this horizontal line, or the so-called optical axis. And therefore, this angle for the center ray must be equal to that angle. So now we considered more triangles. We consider this triangle between O prime and A, or between the 2 object points and the point at the center of the mirror. And we also consider I prime A, or the 2 image points at that same point at the mirror. And now we observe that all 3 angles are similar now. This angle must be equal to that angle because of the law of reflection. And this angle is a right angle by construction, and this angle is a right angle by construction. So we have 2 angles that are the same, and therefore the 3rd angle must also be the same. However, the 2 triangles are not congruent. They are quite obviously different sizes. They are just similar to each other, and that means that I can take the equivalent sides and form ratios. H0, which is the height of the object, divided by hi, which is the size of the image, must behave like the distance from A to O, which is the object distance, to the distance A to I, which is the image distance. So we can form this ratio equations. Now we look at another set of triangles. This one, that is formed with the same 2 points, but now with the focal point as the 3rd one. And that one. And we find that those two triangles are also similar. First of all, this angle must equal to that angle because that's just a straight line and this is a straight line. So those two opposing angles must be the same. Then again, by construction, this angle is a right angle and this angle is a right angle. And therefore, those two triangles are also similar and we can form a similar ratio. So this side is the image height. The reason why it is the image height is because this is a focal ray and it gets reflected parallel. So if this is the image height, then this has to be also the image height. The equivalent side for the other triangle, for this one, is the object height. And I can relate that ratio between object and image height to the distance OF and the distance FA. Those are equivalent sides for that triangle. The distance FA is just the focal length, and the distance OF is the difference between the object distance minus the focal length. So I get this ratio. And with some mathematical gymnastics, you can actually solve those equations. The HO over HI falls out. I can directly set D0 over DI to this ratio. And I get the so-called lens equation, which relates inversely the focal length to the inverse sum of the image and the object distance. Moreover, we can define a magnification, which is the ratio of image over object height. That must be equal to the ratio of image distance over object distance. And by convention, we insert a minus sign in here because this image is upside down compared to the object. And that's why we insert a minus sign in there. Those two equations help you understand all kinds of mirror images. It is valid for concave mirrors. In that case, the convention is that radius and focal length are considered to be bigger than 0. Convex mirrors, in this case, they are smaller than 0. As well as plane mirrors, in which case 1 over the radius and 1 over the focal length is considered to be 0, or the radius and focal length is considered to be infinite. It is valid for real and virtual images, for upright images, where the image and height and the object height have the same sign, and inverted images where they have opposite signs. It's valid for objects and images in front of the mirror or behind the mirror. And if there are multiple mirrors, one can apply this lens equation or this mirror equation in sequence. So we can first consider the first mirror and then consider the second mirror. So the image of the first mirror becomes the object of the second mirror. Finally, the ratio M is called lateral magnification. To make this equation work for you, you have to pay very careful attention to the signs, or you get it wrong. Let's play with this equation a little bit. And one can place a mirror here, and one can change the curvature of that mirror. And for example, we can add a beam, and we see that how the beam gets focused into one focal point. This applet doesn't consider spherical aberration, so it's actually perfect. We can also see what happens if the beam comes at an angle. And in that case, the rays still get concentrated into one point, but that point is no longer on the symmetry axis, which is called the optical axis, but somewhat above. The focal distance doesn't change. It's just the focal point gets moved up or down when I'm pointing the beam in the downward direction. I can erase this again. I can put diverging rays in there as well. So here's a bundle of diverging rays, and the divergence actually changes from the effect of the mirror. Or I can put an object like this, and we see an image forming over there using 3 rays, the parallel ray, the focal ray, and the center ray. And we can see what happens if we move the object further away. The image gets closer and closer to the focal plane of the mirror. And if I move in the opposite direction, eventually they're at the same position. This is exactly when the object is radius away from the mirror. So if the distance between object and mirror is 1 radius. And then as I approach even closer, the image gets further and further away, becomes also bigger and bigger. And eventually it becomes a virtual image. We move the mirror around a little bit. In this case, just like for the virtual image on the plane mirror, there are no actual rays coming from the image itself. It is just abstraction of us seeing the image. And the virtual image, as you see here, is upright compared to the original object. And the virtual image is also bigger for the concave mirror, is bigger than the object itself. And as you approach the focal point, the image again moves further and further away and also becomes bigger and bigger. So let's just consider one example here. So let's assume we have a 1.5 centimeter high diamond ring that is placed 20 centimeters from a concave mirror with radius of curvature of 30 centimeters. And the problem is to determine A, the position of the image, and B, its size. So for part A, we first calculate the focal length. That's half of the radius. So the radius of curvature is 30 centimeters. Divided by 2 gives us 15 centimeters for the focal length. And now we use the lens equation. And that gives us the relation between image distance, focal length, and object distance. And if we solve for 1 over the image distance, we get 1 over the focal distance minus 1 over the object distance, or 1 over 15 centimeters minus 1 over 20 centimeters. And that results in an image distance of 60 centimeters. And since the sign is positive, that means that the image appears in front of the mirror, not behind. And now we can calculate the magnification, taking the ratio of image and object distance with a minus sign. And that gives us a magnification of -3. And since the magnification is negative, it means that the image is inverted. Multiplying the factor of -3 with the 1.5 centimeter height of the object or the ring gives us minus 4.5 centimeters. So the image is actually bigger than the ring itself. And just out of curiosity, if we change this problem, and instead of placing it at 60 centimeters, which was the image distance of the previous problem, what happens then? The equations are exactly the same. Now we take the difference of 1 over 15 centimeters minus 1 over 60 centimeters. We get as an image distance, the distance where the object was before. So if you place an object at its image, then you will find an image where the object was originally. And that is because light rays are reversible. It is not true for the magnification, though. In this case, the magnification is going to be minus 1 over 3. And since the original ring was 1.5 centimeters high, the image is now only 0.5 centimeters high. But image and object just trade places if you move one to the position of the other. So thank you very much.